We want to look at now functions where theta is a function of r. So let's let theta equal h1 of r, or theta equals h2 of r. So it could be literally just theta equals r, or something like that, or theta equals r squared, or it could be different things. Not really done as much. Usually it's r as a function of theta, but now we want theta as a function of r. So they're continuous functions. We're going to suppose h1 of r is less than or equal to h2 of r if r is between a and b. So here's your radius, here's your a to b. And so you have that this function h1 is less than this function. So that's the orientation kind of concept that we look at. And then we do the same type of partition, and I'm not going to go through all those details, but you do the same setup. You do the limit of the partition approaches 0 over the sum of all the k's. And I wrote that as a double sum, which you can do that. You can add up the lengths of one side and then the other side. And then it's r dr d theta. You end up getting this extra factor of r in there because it's the average radius, same concept, because those are, again, polar rectangles. It's the same description or same concept of those polar rectangles, like that. So then it's the same kind of thing. It's just that you have now d theta dr. So it's the integral from h1 of theta to h2, and then from a to b. So let's look at an example of that. So this is find the area of the region R bounded by the polar axis and these functions. So let's take a look at this example. So find the area of the region R bounded by the polar axis, R equals 1, R equals 2, and the spiral r theta equals 1. And we're going to do that from theta equals 1/2 to theta equals 1. Now this takes a little review and stuff to set this up, but we have theta is 1 over r. And you may want to check out what the spiral looks like, but it's basically you got your polar axis, and it essentially looks like this. And then you go from 1 to 2 as your arcs. So those are your arcs going like this. And so this is the region that is in question that we want to find right here. This is your region R. Okay, so that's your R. And so your polar rectangles are like this. And then they're the same type of sectors. So in this format, you're going to go from from here, so from theta equals 0 to theta equals 1 over r. So it's going like that. And then you add that up, add these up from 1 to 2. So A, let me move this over a little bit. Okay. So area is going to equal the integral from 1 to 2, integral from 0 to 1 over r, and it's r d theta dr. So just keep in mind the direction is from here to here instead of here to here first. So it's the first value. So let's integrate. So integral from 1 to 2. And then it's r theta 0 to 1 over r dr. And then this actually becomes nice and easy when you substitute. So now you're substituting for theta. So r ends up being gone. So it's just integral from 1 to 2 of dr, which is just 2 minus 1, which is 1. So the area of that is 1, which I kind of find strange, actually, that that area is 1, even though that's an arc. Anyway, all right, so that's theta as a function of r, excuse me. Now let's look at volume. So this is the last thing. We're going to do volume in with a region and double intervals, but then we'll kind of be able to go into, we're going to do triple next. But that, I might post that this week. I may not, but this is enough for the week, basically. So last example, and this is a convert case where you want to convert to polar. So you'll see what I mean in a second here. So find the volume V of the solid bounded by z equals 4 minus x squared minus y squared. And the xy plane. And that's when we say z equals equal to 0. So what is the first thing we want to do? It is sketch. Yes, we need to sketch everything. So we want to sketch z equals 4 minus x squared minus y squared. So what is that again? Yes, that is a paraboloid. It looks like that. So and it's chopped off by z equals 0. So let's sketch that. So I'll do the axis first, like this. And then y. So x, y, z. And we have, so it's up 4 units, so 1, 2, 3, 4. Let's just go to here and call it 4. Doesn't really matter. So you got your paraboloid coming down like that. Then you have your circle down here. It's going to look something like that. So at 0, so if we just say this is 0, you can see that it's going to be radius 2. So we know that this is going to be 2, and then that would be 2. And then it goes, if you went back, which we're not, but if you did, it would be negative 2 and negative 2. So our region in the xy plane then is this. So this is our region in the xy plane. And so that's my r that I'm going to integrate over. So it's going to be your dA is partitioning that, right? So you're going to partition that whole thing and then times the height. So the height of that thing, right, is going to come up. So you have little rectangles down here, And then you're going to go up to the surface like that. Okay, so that's what you're going to get, and you add all those up. So you got to think of it as volume is a double integral over the region. So you're adding up all that whole region. And then the function is your z, that's your f of xy. So that's 4 minus x squared minus y squared. And then dA, your delta a's are these little rectangles down here. So the regions, though, is that circle. So you want to draw another picture, diagram, not really diagram, I guess. You want to draw another illustration in the xy plane, whatever you're integrating over. It's close enough. So in the xy plane, you have this region. When you set z equals 0. So when z equals 0, we end up with 4 equal to x squared plus y squared. So it's a circle radius 2. And so you can break that up into the top and bottom if you wanted to. I mean, you could solve and go basically like this from the bottom half to the top half. So this would be a representative rectangle. So you could do that, which we're not, because that would be ridiculously difficult. But that is y equal to the positive square root of 4 minus x squared. So and then the bottom half would be negative. So this one would be y equal to negative the square root of 4 minus x squared. And you would integrate from lower to the top from -2 to 2. So if you set this up in rectangular, it would look like this. And you wouldn't have to do this, right? You wouldn't have to show this step necessarily. I just want to show it to you. It would be negative square root of 4 minus x squared to the positive square root of 4 minus x squared from -2 to 2 of the function. The function is the top of it, right? 4 minus x squared minus y squared. And then that, so this is y equals and y equals, so that would be dy. And once you substitute in for your y, then you have just x, right? So then this is dx. A little, I wouldn't call it a little thing you have to look for or kind of think about is look at your outside limits and whatever those values are. So this has to be x is -2 to x is 2. That lets you know what the outside limit is. And you kind of work backwards to figure out your inside limit. If you're not clear, if it's not clear what that is. So you could integrate that, but if you change to polar, you can do it a lot easier. So you just integrate around the circle. So that's what we want to do. So you want to change the polar, and then you can integrate around the circle using a polar rectangle like this. So now for a polar rectangle, you're going from 0 to 2, and then 0 to 2 pi all the way around. So instead, you can say this is equal to the double integral. And then we have r goes from 0 out to 2. Your theta is all the way around the circle, so that's 0 to 2 pi. And then now for the integral here, you can substitute in directly. That's x squared plus y squared. So that's just r squared. So you get 4 minus r squared. But then what do you need to put in for your polar situation? you need that extra factor of r. So it's r dr d theta. And then that becomes just a polynomial. So it's just distribute this in to each term, and you have a polynomial. And you can simplify it. So I have a couple steps that I did. So I think I just distributed for you. So you're going 0 to 2, 0 to 2 pi, and then 4r minus r cubed dr d theta. And that's just a simple polynomial to evaluate. So try that now and evaluate it. And you should get 8 pi. So next, what we're going to look at is triple integrals. So basically, we'll look at a triple. We're going to define it, but so this same setup, basically, instead of putting in the integrand like this, what we'll do, you basically go 0 to that 4 minus x squared minus y squared. And then you put in the same other limits here and here. And then you say dv. Okay, so that's going to be a triple. So you basically can, and that's really what you're doing, right? You're really, if you just put that in, if you put this in and subtract the lower, but the lower is z equals 0. So whatever the lower is, that's what you would put here. So it ends up being the same thing. So we need to first go through a little bit of the theory and define that, but then you could do the same problem with triple. So the way I'm looking at it, because if I do this stuff, there's really no difference between this triple and this double integral.